everyone. So today we're going to be going over the first question from USACO Bronze, which is the palindrome game. So let's read over the question first. Bessie and Elsie are playing a game with a pile of stones that initially contains S stones. The two cows alternate turns with Bessie going first. When it is a cow's turn, she must remove X stones from the pile, where X is any positive integer palindrome of the cow's choosing. If the pile is empty when a cow starts, that cow loses. So basically what a palindrome is when you flip the number and it is the same number. Basically, for an example, 11 is a palindrome because if you flip 11, it'll still be 11. If you 121 is also an example because if you flip 121, it'll still be 121. And an example of that is not a palindrome is 990 because if you flip it, it'll be like 099, which is not the same as 990. So yeah, there are T independent test cases, and for each test case, print who wins the game if both cows play optimally. The first line contains T, which is the number of test cases, and then the next T lines describes the test cases, one line per test case. And each test case is specified by a single integer S, which is the number of stones. So that is the input format, and then the output format will just print if B if Bessie wins the game under optimal play, and E if there's no way for Bessie to win. So yeah, sample input, we have 3, and then 8, 10, 12. So 3 is the number of test cases, and we see that there's 3, and then we have 8, 10, 12. So in the first test case, or for 8 stones, Bessie will win because she can just take all the stones because it is a single digit number, so it is a palindrome. For 10, however, Bessie cannot take all 10 stones as like it is not a palindrome, and so she is forced to take a single digit number, in which case Elsie is left with another single digit number, and so Elsie will win the game. And for 12, the most optimal way that Bessie can play is by taking 2 stones, and then Elsie is now left with 10 stones, so she can take a single digit number, or she is forced to take a single digit number, and then Bessie can take the other single digit number. So to restate the question, we have a pile of S stones, and then Bessie and Elsie takes turns removing the stones, and then they can only remove a number of stones that is a palindrome. And then Bessie always goes first, and then the player who cannot make a move loses. And our goal is to determine who wins if both play optimally. So in order to approach this question, we're going to define winning positions and losing positions. So basically, winning position is when Bessie has a way of winning, and when there is no way for Bessie to win, like when there are 10 stones, it'll be a losing position. So if we think about this, numbers 1 through 9 will always lead to a winning position as it is a single digit number and Bessie can just take all the stones. And at 10, again, it is a losing position because Bessie has no way of winning. She has to take a single digit number, and then Elsie can take the other single digit number. Let's think about after number 10. So for 11, it is a palindrome, so Bessie can win. And for 12, as I explained, she can put Elsie in a losing position, which is 10. So she just takes 2 stones, and then Elsie is left with 10 stones, which there's no way, or yeah, there's no way for her to win from there because she has to take a single digit number. So we see that that is a pattern from after 10. So from 11 to 19, Bessie is winning because she can just leave Elsie in a position where she has to be left with 10 stones, and then Bessie wins automatically. So now let's go over the actual code. We're going to approach this problem using dynamic programming. So dynamic programming is when we try to find a pattern and try to solve it from there, basically. Like we try to remember what like the output of a certain number is, and then from there we try to solve it, if that makes sense. And so yeah, back to the code. We have T equals int of input. Again, that is the input of the number of test cases. And then from there, we're going to iterate through T, and then we're going to output like the number for each number of test, or each number of stone, which is a test case. So we have S is equal to int of input. Again, that is the input. And then we're going to initialize an array where it is just all going to be false for now. So we have when equals false times S plus 1. After that, we're going to iterate from 1 to s plus 1 because it'll end at the second part of this parameter, it'll end at s because it is not inclusive. And then we have another for loop inside of that, which is from 1 to 9, because we know that all numbers 1 through 9 is a palindrome, in which case um, Bessie will win. So it is a winning position. So from our pattern earlier, we saw that if Bessie is able to make put Elsie in a position in a losing position, then Bessie will win. So we put that if win of I minus j is false, then Bessie will be able to win. So she will be able to be in a winning position. And then once we find that number where Bessie is able to put Elsie in a position where she has to lose, then we'll just break because we already found a solution where Bessie can win. But if we're not able to find any number from 1 through 9 where Bessie can win, or 1 through 9 where Bessie can take the stones and then put Elsie in a losing position. Unfortunately, Bessie cannot win, so we have win of that index equals false. And that at the end, we're going to print B if win of S is true and E if win of S is false. So let's try printing this out. So again, earlier the test case was 3, and then we 8, which is B, that's good. 10, which is E, that's good. And 12. So yeah, if we want to, we can do another test case, say for example, um, let's do 4 test cases and then we have 2. So B, Bessie will win. Let's do a number like 19. We know that like 19, Bessie will win again. Maybe like 300. Cool, we find out that Elsie will win. And lastly, maybe like 4,000 and 12. Yeah. So eventually, once you get the hang of this, you'll find out that every multiple of 10 actually puts Bessie in a losing position. And we see that from the pattern where 10 is like the case where Elsie is guaranteed a win. And from that logic, we see that if it's a multiple of 10, there is no way for Bessie to put Elsie in a position where she's guaranteed to lose. But yeah, that is how to solve the palindrome game. Hello everyone, I'm going to be going over problem 2, which is called a milk exchange from USACO Bronze. So Farmer John's n cows are lined up in a circle such that for each I in 1, 2 to n minus 1, the cow to the right of cow I is cow I plus 1, and the cow to the right of cow n is cow 1. So it is like a circular motion. The ith cow has a bucket with the integer capacity I liters. All buckets are initially full. Every minute, the cows exchange milk according to string S1, S2 to Sn, consisting solely of the characters L and R. And if the ith cow has at least 1 liter of milk, she will pass 1 liter of milk up to the cow to her left. If S of I equals L, to the right, if S of I equals R. All exchanges happen simultaneously, so it can like receive and give at the same time. If a cow's total milk ever ends up exceeding A of I, which is like their capacity in liters, then the excess milk will be lost. So FJ wants to know, after n minutes, what is the total amount of milk left among all the cows? So the input format is the first line contains n and m, which is the number of cows and the number of minutes. And then the second line contains like the characters L or R, which is the direction that each cow will be moving. So like the first cow will, like for example, for the first sample, the first cow will move it to the right, the second cow will move it to the right, and then the third cow will move it to the left. And then the third line is the capacities of each bucket. So first cow has 1 liter, second cow has 1 liter, and then the last cow also has 1 liter. So the output format is we're going to output an integer to see the sum of milk among all cows after all the transfers after n minutes. So yeah, let's look at the first example. We have 3, 1, which is 3 cows and then 1 minute, and then we have RRL, and then we have 1, 1, 1. again. So the passing step, so the first cow will pass it to the right, so to cow two. The second cow will also pass it to the right, so cow three. And then the third cow will pass it to the left. So after 1 minute, after they pass it all, the first cow will be left with 0 liters because the first cow passed it to the right, didn't receive anything. The second cow he it receives from the left cow and the right cow, but so it's at 2 liters. But since the capacity is 1 liter, like the 1 liter will be lost. So the second cow is left with 1 liter, and then the last cow, it receives from the second cow and gives to the second cow. Yeah, so they like trade. So it is left with one. So again, the first cow is left with 0, the second cow is left with 1, and then the last cow is also left with 1. So the output would be 2. Um, for here, for the second example, we have 5 cows after 20 minutes, and then we have L, 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 and then we have um 3, 3, 2, 3, 3. So I mean, because they're all passing it to the left, they'll always just give and receive 1 liter each minute. So it is actually unchanged. So it'll just be 3 plus 3 plus 2 plus 3 plus 3, which is 14. Yeah. And then yeah. So what is the key approach to this question? So when does the milk get lost? So if a cow is surrounded by cows that's passing milk from its both sides, then obviously it'll be lost because it'll overflow. Yeah, so each minute it'll like lose milk every time. And then so how we're going to approach this question is we're going to identify the cows that will keep losing milk and then compute how much milk will be lost from their supply chain, and then subtract the minimum of the total milk that can be lost and M from the initial milk sum. And M is the amount of minutes. Let's go ahead and like look at the code. Yeah, here's the code. So the first line we have define compute milk remaining with the parameters n, m, sa. So we're just defining a function that we'll be using to solve this problem. So n again is the number of cows, m is the number of minutes, s is a string representing each cow's passing direction, which is L or R, and then a, which is a list of integers representing the capacity of each cow's bucket. So the first line we have total milk equals sum of A. So we start by calculating the total amount of milk initially available, because all buckets are full in the beginning. And then we're going to iterate through from I to the number of cows to see where milk loss might happen. So yeah, we have an if statement right here. If S of I is R, and then if S of I plus 1 mod n is left, we're going to do J equals 1 minus 1 plus n. So we're going to start moving to the left. And then we have a lost milk equals 0, which is to keep count of the lost milk. So basically what this if statement is doing is we're going to see who is or like which cow is losing milk. So if a cow at index I is passing to the right, and then the next cow, so I plus 1 is passing to the left, that means that the cow will receive milk from both sides. It's going to lead to overflow. And then we have mod n here because it is like a circular pattern. We're going to ensure that like if I plus 1 does exceed n minus 1, it's just going to index at 0. So it'll go back to 0 cow. And then we set j as the previous cow, so I minus 1. And then lost milk obviously is keeping track of how much milk this chain will lose. So yeah, next we have a while loop. So if the previous cow j also passes to the right, because we set j to the previous cow, which is like the cow to the left, it'll contribute to the loss. And we keep moving left to see through all the R cows. Like, so as long as S of j equals R, we're going to keep iterating through the left to see how much milk is lost. And then at the end, we have total milk minus equals minimum of lost milk and M. So since we can only lose up to n liters per deficit cow pair, we're just going to use the function minimum to see like if lost milk is smaller or m is smaller, and then subtract that from the total milk. So yeah, and then similarly, we're going to do this on the other side as well. It's basically like we're going to check the left chain. So this is basically the same code, but for the other side, if I is L, or the S of I is L, and then S of I minus 1 is right, then it's going to lead to overflow. So we're going to set the cow to the right, and then again keep track of the lost milk. So this is obviously the same code. So while S of j is equal to left, we're just going to keep moving the cow to the right, and then keep track of the lost milk. And then at the end here, we have total milk minus equals minimum of lost milk in M. Again, the lost milk is capped at M, the number of minutes. So we're going to subtract that from the total milk. And then at the end, we're going to return total milk, which is going to give us our final answer. So this code right here is just so that our function can read the input that is getting inputted. And then this right here is the line of code that is actually going using the function to give us the output. So let's try running this code. And then our first example was this one. So again, because we have 3 cows and then 1 minute, and then we have RRL, as I explained earlier, we're going to get left with the first cow having 0 liters, the second cow having 2 liters, sorry, 1 liter because it'll overflow, and then the third cow also having 1 liter because it's just trading from its left cow. Yeah, so it should output 2. There you go. And then let's do the second example, second test case that is provided. Let's run it again. And then the last test case, which is this one. Great. So yeah, we passed all the test cases, and this is how you do question 2. We're going to go over problem 3, which is maximizing productivity. So the question says, Farmer John has n farms numbered from n1 to n. It is known that Farmer John closes farm at I at time C of I, and Bessie wakes up at the time S and wants to maximize the productivity of her day by visiting as many farms as possible before they close. She plans to visit farm I on time T of I plus S. Bessie must arrive at the farm strictly before Farmer John closes it to actually visit it. So Bessie has Q queries. For each query, she gives you 2 integers S and V. For each query, output whether Bessie can visit at least V farms if she wakes up at time S. So the input format is the first line consists of an NQ. So N is the number of farms, and Q is the queries. And then the second line consists of C of I, C of 2, all the way to C of N. And that is when the each farm closes. And then the third line is T1, T2, like all the way to T of I, and T is the travel time. So yeah, so the next Q lines each consists of 2 integers, V and S. So V is the number of farms that Bessie wants to visit, and then S is the time that Bessie wakes up. So to go over it again, so what is Bessie trying to do? Bessie wakes up at time S and she decides to visit farm, and she will arrive at the farm, right? So she can only visit the farm before it closes. So we should subtract T of I minus C of I. Yeah, and then for each query, we need to determine if there is at least 3 farms that Bessie can visit before they close. If yes, print yes, otherwise print no. So let's go through the example. So we have 5 farms and 5 queries. And then each farm has a closing time of 3, 5, 7, 9, 12. And then each farm also has a travel time of 4, 2, 3, 3, 8. So we want to subtract the travel time from the closing time to see if Bessie has enough time to visit that farm, right? So let's see, 3 minus 4 is -1, 5 minus 2 is 3, 7 minus 3 is 4, 9 minus 3 is 6, and 12 minus 8 is 4. So now we have -1, 3, 4, 6, and 4. And she wakes up at 5. So we need to see um, if the calculations that we did has any number that is greater than 5 and at least one of them. And we see that again um, the calculations would bring us to -1, 3, 4, 6, and 4. So since we do have 6, which is greater than 5, it'll output yes. So for the second one, she wants to visit at least 1, and she wakes up at 6. So again, we do the calculations, and it's the same thing, right? So it's like -1, 3, 4, 6, and 4. And there is no number that's greater than 6. So unfortunately, she is not able to visit at least one farm. And then so on and so forth. So since again with the same numbers, -1, 3, 4, 6, and 4, we have three numbers that are greater than 3, which is 4, 6, and 4. So the next line of code is will output yes. And then as she wakes up at 4, there are four numbers that are greater than 2, which is 3, 4, 6, and 4. Um, so this will output yes. And then finally, for the last one, she wants to visit all 5 farms, but she wakes up at 1. However, not all 5 numbers after the calculations are greater than 1. So this will unfortunately output no. So yeah, the key takeaways from this is that we want to transform the condition. So instead of checking each farm individually, we just compute C of I minus T of I, and then we're going to sort it so that it is in order. And then we're going to use binary search for this problem. Instead of iterating over all forms for each query, we could just use bisect right to eventually find the number of valid farms in that she can visit. And then sorting the value first makes it easier to answer each query quickly. So yeah, to approach this problem, we're going to compute C of I minus T of I for each farm, or for all farms, and then we're going to again sort the array that is given, um, and then binary search, and then check if at least V farm satisfy the condition. So yeah, now let's look at the code. So we're going to import these two so that we can use it in our function. So these lines of code is for the code to like actually read the input. Again, N is the number of farms. Q is the queries, and then we have C, which is the list of the time that it closes, and then T, which is the list when the travel time. So yeah, so again, the first step is to compute C of I minus T of I for each farm to see if Bessie has enough time to go visit the farm. So we're gonna do diffs equals C of I minus T of I for I in range of n. So we're going to iterate from I to n and then compute C of I minus T of I. And then we're going to do diffs.sort, and then this is going to sort the array in order so that it is easier for searching. So yeah, next, finally, we're going to process the queries. So we have output equals an array. And that is what our output is going to be, obviously. And then so we're going to for loop iterate through the queue, which is the queries. So we're going to split it so that we can read each number that is on the line individually. And then next, we're going to binary search for the first element that is greater than s because that's all we care about, right? So index equals bisect right. We're going to bisect right the values that we got in diffs and s that is greater than s. Yeah. So we have the valid farms that she can go to, and the last step is to see if that is greater than V, which is the goal number of farms that she wants to visit. And then, yeah, so if it is greater, then we'll output yes, and if it's not, we'll output no. And then just for the sake of the formatting, we do have to have this last line where it'll just create a new line every time we have like yes or no. So yeah, let's run the test case. And I'm just going to copy and paste the sample input. Yeah, so we have yes, no, which is exactly what we want. Yeah, that is how you solve maximizing productivity.